I'm just providing a bit of background. But for kind of starting off that project, we developed a pilot system using Sentinel-1 radar data and tested that in an area of Madagascar. And with that, we kind of tested and developed some ways for processing Sentinel-1 data on the cloud and Google Earth Engine. And so that's what I'm hoping to go through today. So as just a bit of logistics, we have 2 hours set aside today. I don't know if we'll use the whole time. I'm recovering from a cold, so I'm not sure how long my voice is gonna be able to last, but we could kind of see how far we go. I have shared a document that provides instructions for running code on Google Earth Engine. And that's something that we'll go through. That's also something that will last after today. So if you're not able to follow along today, or you want to go back and try it later, that's not going anywhere. So yeah, so that'll be there to do. Please let me know if I'm going too fast. I know that especially I'm speaking in another language, and we're really lucky to have Kathleen here doing the translation, but I know that it's inevitable that some of the technical terms could get lost in translation. So please let me know if you want me to repeat anything or slow down or speed up or anything, please feel free to just jump in. All right, and with that, I'm gonna dive into a little bit of a presentation here to start. So before we got started on the actual exercise, I wanted to just give a little bit more background on the pilot study that we conducted this year and the paper that we submitted along with that work. And I apologize, this is all in English. The actual material on Google Earth Engine, I have translated, so it's both in just English and French. But for this presentation, I'll go slow. And so the title of the paper that we submitted is called Timeliness and Force Change Monitoring, a new assessment framework demonstrated using Sentinel-1 and a continuous change detection algorithm. So that's a lot of words. And what that means is basically two things. We were, on the one hand, trying to develop a force change monitoring algorithm, but we were also interested in really how we could evaluate such an algorithm. And so kind of the underlying issue here is that all of the methods that exist in the literature for doing accuracy assessment or any form of evaluation of a change detection algorithm, it really is just based off of spatial accuracy. And what we're really interested in is, yes, accuracy matters, but for an early warning system, so does speed. And there isn't really a system in place or an existing approach for evaluating the speed or the timeliness of an algorithm. So how fast could it detect an alert and how accurate will it detect an alert? And so we chose a pilot location in northeastern Madagascar. I quickly came to learn that, as I'm sure all of you are very well aware, this is one of the cloudiest places on Earth. It's mountainous, and from a remote sensing standpoint, it is a very challenging place to work. Once again, I'm sure I'm telling you things that you already know, but this is what I came to learn doing this work. And so, due to the clouds, um, it became apparent that we would in some way need to use radar data. And so that's why we developed a system based off of Sentinel-1. So Sentinel-1 is a European sensor. It's called a C-band radar. That's just the type of radar sensor it is. In the top right, you'll see where it has coverage in the world. And basically what this figure is showing is that there are different modes of acquiring data based off of the application for that data. Over most land surfaces, it's the same. And that's basically we'll capture data with dual polarization and at 10-meter spatial resolution. The one big advantage of radar data, at least when monitoring forests or working in the tropics, is that it's not affected by clouds in the same way that an optical sensor like Landsat would be. So people often say that radar data could see through clouds. What that basically means is that it could penetrate through clouds and observe the surface and record data regardless of the cloud cover. It will be affected by moisture conditions and other sources of noise. So the data can be kind of messy. There could be like a salt and pepper effect or a speckle. And there are ways of reducing that we'll go into today. One really useful part of Sentinel-1, for us at least, is that there are new observations every 6 to 12 days. So if you think of creating a monitoring system, you want repeated observations, and ideally you want frequent observations. So it's a useful sensor in that regard. And it's probably the first radar sensor that has all of these characteristics that are ideal for forest change monitoring. You know, it's medium spatial resolution, and it is freely available for us, and it's frequently observed at the same location. So we applied Sentinel-1 to an algorithm called continuous change detection and classification, or CCDC. CCDC has been used a lot for land cover monitoring using a satellite sensor called Landsat. And so that's an optical sensor, which means that it cannot see through clouds. So we basically substituted Sentinel-1 data instead of the Landsat data to see if the same exact algorithm would work. And to our knowledge, this was the first attempt to do this with this specific approach. And it generally, we found that it works well. And so the basic idea is that with the algorithm is that it uses all available data, so all data in an archive. And for every location, it fits a model to the time series data for that location. So there's an example here on the right. This is a forest change event in Madagascar. You'll see that between December 2019 and October 2020, there's some sort of change in this patch in the middle of the figure. This plot down here, this is a time series plot. And every dot on the plot, every gray point, that is a different observation for the location in this cross in the middle of the images. And so this is vertical horizontal polarized backscatter. And basically the way that this model works is that it fits this red model to the data. It tries to predict future observations. But when the real observations are different, it flags a change. And so it creates these red pixels in here, which are the change alert. And what's important here is that all of these points, all of these images need to be processed to the same standards. And that's done on Google Earth Engine. And that's what we're going to be doing today and seeing the steps along the way. I should say that another focus of our study was to create an assessment framework. And so we generally think of accuracy as what's an accuracy of a map? What's the omission and commission error? But that tells us nothing about how quickly an approach could develop that map. And so we developed this framework for adding, in addition to accuracy, what's the timeliness of a system? Because we have to acknowledge that for an early warning system, it will really only be useful if it could operate quickly. And so we need a method of evaluating that. And I won't go into the details here. I'm happy to share the paper with anyone who has not seen it yet. although it's still under review. And we're not going to go through this process today, but I'm happy to elaborate on this point at all. But yeah, so the two parts of the study were the Sentinel-1 monitoring system, which we're going to go over today, and then the assessment framework, which we'll not go over today. So what I hope to accomplish today, I've put together a tutorial for processing and visualizing Sentinel-1 data on Google Earth Engine. I want to go through the whole, every step in the process and take a little bit of time at looking at what that step does. I know that at least some people in the group don't have experience with Sentinel-1 data. And although it's tempting to just jump towards the end of the process and making maps of forest change, I think it's really important if you're going to use this data to have a good understanding of what it goes into actually making it usable. When I started using Sentinel-1, I did not take the time to do that. I just jumped into using processed data. And I think that was a mistake. And that it's complicated data. It could be really useful, but it could also be very frustrating and hard to use at times. So that's why I think it's really important that we spend time really looking at what the data is and how we can make it into a usable form. And if we have time, the end of the tutorial is actually the first step in making a map of change in our proposed alert system. Okay, any questions on that? Once again, feel free at any point, just turn on your microphone and get my attention, and I'm happy to go over something in more detail, clarify anything. So in the chat, I posted a link to a document that has steps for the tutorial for today. Before we, it gives people like random names. And so I just saw that a pumpkin just started reading it. Anyways, before we start going through this, I want to point out that you could translate this page if that helps. I've used documents written in other languages translated to English before. It's not great, but it's surprisingly good. And you would do that by going to Tools and then Translate Document, and then choosing your language, and it will make a translation. Okay, so hopefully everyone was able to create an Earth Engine account if you do not have one already. If you do not have an account, there's a link here to sign up. It could take a little bit of time to get into the system. So if you don't have an account, I would suggest following along today, creating your account and going back through it later when your account is activated. So the code for running this tutorial could be found in this link here. So when you copy this and go to the link, you'll be taken to Google Earth Engine. If you have not used this before or it's been a while, this is what's called a code editor. And this is basically one way of making use of Google Earth Engine. It's a very convenient way because this page allows you to write code, run that code, execute the processing on Google servers, look at the results on a map, save the results as files either in Earth Engine or to Google Drive, and also save your code so that you could use it again later. And the code that you save is organized in folders, or they're really repositories. And so the repositories are under the scripts, and these basically hold scripts for specific projects by certain users. You should have an owner folder here that has any repositories that you've created. There's also writer. So these are repositories that you didn't create, but you have permission to edit. So if Yang and I are working on a project, he could create a repository, but give me permission to actually edit the files. Finally, there's reader, which basically is any repository that you could access, but you can't edit. And that's what the repository we're going to use today should be for you. It should be under reader. Because I created it, for me, it's under owner. But the repository is named users, users Bullock E. That's me. That's my username. And then tutorials. And I should point out that I tried to be very descriptive in the tutorial with how to do all of these steps. So for example, you'll find the repository as I mark in the tutorial here. In scripts, for you, it's under reader. And then the repo is tutorials. And then the folder within that repo is called Sentinel-1 in Madagascar. There should be only one script in that folder, and it's called one preprocessed Sentinel-1. And when you click that, you should see this code editor here fill with stuff, with writing. And all of this in here, this is code for doing all sorts of analysis. And this is what we're going to be walking through today. So the way I have this set up is that I have written the code in a series of steps. So I believe there's 12 steps. But if you just run the code as it is, nothing happens. And that's because by default, the code is commented out. And so just going to the tutorial, I've described in this section under tutorial how to go about actually running the code. I'll try not to flip back and forth too much. I basically just want to make sure that you know that everything I'm saying is also going to be in that document for later. So in order to run code, you need to uncomment the code. And so everything with 2 forward slashes, this is code. And so these forward slashes, this is telling Earth Engine, don't run these lines. This is a way of commenting your code so that it's there, but it won't actually be executed. And it's easy to tell that something is commented because it's green like this. So above this, there's a bunch of lines that are inside these asterisks. And this is not code. This is not something that we ever want to run. This is just a description of what this step is doing. For example, this step is called Madagascar extent. And what it is doing is calculating the extent of Madagascar and adding it to the map. I've translated all of this documentation in the code. It's using Google Translate, so it might not, it will not be perfect. But I thought that it might help a little bit here. Okay. So to summarize, this writing in the asterisk, this is documentation that we're not going to run. This writing that's in front of the forward slashes, this is code that we need to uncomment out, and we do that by deleting the forward slashes. So you'll see that it turns to different colors when I do that, and that signals that it's code that we could run. And you might be asking why I bothered commenting everything out. Why not just provide the code and run it yourself without having to do this extra work? In my experience, it's helpful to have to modify the code a little bit so that you could actually see what the effect is you're having on the results. So this is basically just my way of, without having to actually write code yourself, modify it in a way that you'll actually be able to see what you're adding to the map and what you're doing with the various steps. Okay, so I've uncommented this first section. And the way you actually execute the code is by clicking run. And it might look like nothing is happening. But we'll see if we navigate to Madagascar, that there is this black feature for the country extent. And we just added that with step 1. So hopefully everyone's able to follow along. I'm not able to monitor the chat while I do this. But once again, if you want me to slow down, just either if anyone else sees in the chat, someone speak up, or just turn your mic on for a second and say something, please. It's always a little hard. Sorry, go ahead.
Eric, I will monitor the chat if there's any question.
Thanks, Jan. It's always a little hard being so far away and over Zoom. to know where people are in the process. So yeah, please feel free to speak up at any time. Okay, so step one, all we did was add the Madagascar boundary. I just wanted to demonstrate, very simply how the code works, how the map works. We could turn this layer off in the Layers tab, and it's called Madagascar. This will be how you turn on and off all of your layers later on. This slider is transparency. All right. So the second step is we're going to start building our collection of Sentinel-1 images. And so now there's, I don't know, 10 lines or so of code in here. Oops. We could either manually delete the forward slashes so that we could run this code. Or you could also no, thanks, yeah. You could also highlight it all and use a keyboard shortcut to uncomment everything at the same time. And so on a PC, you can't, I guess you can't see my hands, but it would be Control and / that will comment or uncomment everything you have selected. I don't have an Apple, but I think it would be the Apple symbol plus /. All computers are different, but I do encourage trying this out because it could save you some time. So there are a couple of things that you could modify with this step. Well, really the only thing you can modify is the start and the end time for your collection. And I have it by default to start in January 1st of 2021 and end August 31st, 2021. And what this code will do is it will access the Earth Engine collection of Sentinel-1 data, filter it by our study area, which is the country of Madagascar. Make sure that it has the polarization modes of BV is vertical, VH is vertical, horizontal. Make sure that it's being collected in the 10-meter mode that is present over most land areas. And then filter by the start and end date. If you're ever curious about data on Earth Engine, This first line here, it's collecting all of the Sentinel-1 data that's in this path here. And people from Google really like to point out that if you ever want to learn more about something on Google, you use the search bar. And so if you search for this collection here, you should see under rosters that you get one match, that's Sentinel-1 SAR gridded data. And if you select that, you'll get a lot more information about this collection. I won't go through everything here, but I want to point out that this is a good resource, and it has links to how this collection was made. There are links to tutorials, other tutorials, links to pre-processing articles, information on the bands that it has, and then the metadata. So this is a really good first place to look if you're looking for more information. Okay. But the second step, it will take this collection we just made and add the first image in the collection, the VV polarization and the VH. And when you run this, the Madagascar extent gets re-added to the map. Nothing else happens. And that's because these two layers that were added, you need to turn them on in the layers tab. I have them turn off by default because there are 12 steps, and most steps have one or two things being added. And so by the end, there's going to be a whole lot of stuff, and it's just easier to not have it loaded by default. But I'll turn one of these on. I turn on VH polarization. And so this is just the first image. It's way up in the north. This is just one band. And this is just one image. We want to get from this to a composite of the whole country, and also of a stack of images that we could use in CCDC for change detection. So a very simple way that we could make an image for the whole country is to create a mosaic. A mosaic is a broad term, but what it means in the context of Earth Engine is that it will, for a whole bunch of images for the whole country, where there are overlapping images, for every pixel, it will take the first observation and use that to create a new image that is now the extent of the whole collection. Okay, so that was a little confusing, but it will help to just look at what step 3 will produce. And so if you're calling this in step 2, we created a collection of Sentinel-1 imagery. I'm not going to embarrass myself trying to say French words. This is data in English, données. And so this is hundreds of images. What we're doing in step 3 is mosaicing them. So we're just taking the first image of the collection at each location, stitching it all together, and adding it to the map. So I uncomment step 3, run it again. And once again, I need to turn on the layers because they're not loaded by default. But when I turn on one of the mosaic layers, it'll take a second to load. But it will eventually load an image for the whole country. And we'll get into the difference between these two bands, the polarizations. For now, just note that they are different. So this is just taking, for all of the images, the first pixel for every location and stitching it all together. What we could see in either of these layers is, even if you're not familiar with looking at radar data, this is not a very pretty image. You could see these blocks cutting through the country. This is the effect of the orbit of the satellite. And so all of the images in this orbit here create distinctly different backscatter than the one just to the west of it. So you see these very distinct lines. And I haven't even described what the stretch is. It's going from blue to white to brown. But that doesn't even really matter. You could tell that this is not how, nothing in the landscape creates this dramatic difference here, cutting straight through the country. And that tells me that this very simple way of making a mosaic is not good. Well, it's not sufficient for this purpose, at least. So one reason that the backscatter could be, let me back up. There are a lot of reasons that the backscatter could be different between these different orbits. They were collected at different times. So if there's different moisture conditions or atmospheric conditions, that will cause variability in the data. Importantly, also, they could be collected from different view angles and even viewing directions. So Sentinel-1 has images collected from the descending orbit and also the ascending orbit. And so these different orbits will have drastically different view angles. And at least by default, they could create pretty different data. If you think of any sort of feature on a landscape, whether it's a mountain or a tree or a person, if you're reflecting off of that feature from completely different directions, you're going to get different reflection. And so it's not incredibly straightforward to use data from the different orbits. So what I'm doing here, what we're going to do here, is just calculate which orbital pass has the most data and just only use that one. So in step 4, what this does is calculate a histogram of a metadata value that describes the orbital pass of each image. And it will print that number to the console. And what I mean by that is printing out something is basically communicating the results of a calculation that's not something that could be added to the map. For example, our count of orbital passes. And that's it's printed to the console, which is in the top right of the screen. It says console. And this is where you write things like this. And so this says the number of images in each orbital pass. In the ascending direction, there's 82. In the descending, there's 539. So instead of trying to basically normalize these data together using a complicated procedure, I prefer just to remove these 82 ascending orbit images. And so if you run step 5, all this is doing is filtering our collection on the metadata in which the orbit or the orbital pass is descending. And so in your console, it'll say that between January 1st, 2021 and August 31st, 2021, or yeah, 2021, there are 539 images that we'll be using for the country. Thank you. Yeah, so because the view angle of the sensor will be drastically different. The data will not be comparable, at least directly comparable. So if we're looking at an object from different directions, the backscatter of that object could be dramatically different. So it is essentially, if we're only using one orbital pass, it's essentially ensuring that all of the pixels are being observed from a similar direction and will therefore be comparable observations. Yeah, it's a way of filtering the data to make it a little bit smoother. I should add that there are ways of incorporating the different orbital passes directly. You could normalize the data. I'm choosing not to do that here. For one, there's only 80 or so images, 82 from the other orbit. So there's a whole lot more from the descending. And I don't think it's worth the effort to do that just for 80 images. At least in this context, that's my opinion.
I also put some explanation in the chat. So
thanks, Jan. So in step 6, we do a couple things. We calculate what the most recent image is. So I find myself often when there's a major natural event in the world, I want to look at it under satellite imagery. Or if you're trying to see if there's been a nearby forest change event, it helps to have the most recent image and know when that date of that image is. And so this process will tell us what the most recent image of the collection is and add that to the map. It will also calculate. So right now we have the VV and VH bands. Another way we can look at the data is the difference between the two, or the ratio of the two. Sometimes the difference between these two bands can be informative. And it also allows us to create a color composite with 3 bands. So this step 6 will find the most recent image, calculate the difference between the 2 bands, and add it styled as a color composite. So before looking at the image, on the console, it'll print out the date of the most recent image. And so the most recent image for our study region was on August 7th, 2021, which is 3 days ago. And so this is pretty good, 3-day latency. This means that, if something happened just a couple of days ago, you could likely look up an image associated with it and analyze that image. This is just one image though. And because it's the most recent one, it's, the end of the orbital track for Madagascar. So it's all the way in the corner. Probably the image right here was taken seconds earlier. But technically this is the most recent. And what you can see is now this is a color composite in which I'll wait to describe the colors until we have a better image to work with. So before we made a mosaic of the whole country. And so that was what we were looking at a few minutes ago. And it's pretty noisy. You could obviously see the effects of the different orbital passes. And that is because we were just selecting the first pixel from every location, stitching that together, regardless of what, the normal average state of the backscatter was. We're just selecting the first one. We could also create a temporal composite in which we, instead of taking the first, we take something like the average or the median. And so in step 7, we are going to create a median composite, which for every pixel will take the middle value for our study period of January to August. And so this will once again calculate the difference between the VVE and the VH and display it as color composite. And so we can see that we're starting to get towards what, at least when looking really zoomed out, a more usable composite of the country.
Hey, Eric.
Yeah.
Before we go on to the next step, this might be a good time to give people a little break to catch up and get themselves together and maybe ask any questions or give them time to formulate a question.
Yeah. Thanks for saying that. I think that's a good idea.
So maybe we can, well, I don't know if this is the stopping point, but maybe give people 5 or 10 minutes. Thanks.
Yeah, maybe let's take like 5 minutes here. And as Sean said, give people time to catch up. You can write a question in the chat or say it out loud. This will also give me a minute to go get a glass of water. So I'll be right back. So I'm just curious. Maybe you could just put a note in the chat if this is okay. But I'm curious if anyone has been able to get to the point that I'm at, which is step 7.
It's working for me.
That's good. Oh, good, good. The bluish greenish map, okay. I would guess that is this one. Well, bluish green.
I think it's the median composite.
Okay. Oh yeah, this is bluish greenish. Good. I appreciate the feedback. That's good to hear. Okay, so cool. Okay, so I'm gonna start slowly again. But just a reminder, please, jump in if you want me to repeat anything. So this is an image. It's not, it's not an image that looks anything like what we're used to looking at when we see images. With an optical sensor like Landsat, they observe data as reflectance in spectral bands in a similar way to how our eyes see the world. It's not technically true, but we're able to create images that are similar to what they look like to us in real life. This image is a combination of different bands of backscatter. This is not how our eyes see the world. This is a composite that I think is informative, but it is definitely not straightforward to what the colors mean. There's a tool on the top right of your screen called Inspector. And this really has 2 main purposes. It changes when you click on the map, and it tells you information about the map where you clicked. The first purpose is to give you the coordinates of where you just clicked. So if you want to go look on Google Earth or something like that, this will give you those coordinates. It'll also give you the values of your different layers at that location. And so we have, 6 layers now. And so it'll give us 6 values. So I'm clicking in the middle of the country, and not all of the layers have data there. That recent image that was in the corner of the country, there is nothing there, so there's no value. But for everything else, it'll tell you what, for VV, what the value is for VH. And so this is a way of kind of exploring what the actual data is. We'll get to some more ways of doing this. But we could also, turn off the transparency and try and get a sense of, what the colors represent in the actual landscape. And so one thing that is very clear is that water has very low backscatter. And that shows up as a dark blue. The vegetation, the mix of forests and non-forests, that's this kind of greenish color in here, and that is a higher backscatter. And then the mountains, which I think are a mix of bare and herbaceous, that's kind of in the middle in terms of backscatter, and that's showing up as kind of this purple color. Okay, so one thing that you could see when you zoom into the middle of the country is that you could see the mountains pretty clearly. Radar data is pretty sensitive to the angle of the surface. So if there's a steep terrain, either facing towards or away from the sensor, that will really affect what the backscatter is for that location. You could think about throwing a tennis ball at a wall that's slanted away from you. It's not going to return to you in the same way as throwing a ball at a wall that's completely vertical. So that's similar to the scattering effect of radar. It's even apparent in areas that I wouldn't think of as mountainous, along the coast here. That there's just topography. There's hills and slopes, and we could see that in the data. For some applications, this is okay. For instance, if you are trying to monitor floods or anything related to water, that will probably not be occurring in topographic lands. And it doesn't really matter if there's large effects of topography in your data. However, as we learned doing our pilot study, it can make considerable difference when trying to monitor forest change over very topographic lands. It could basically mean that it could create just extra noise in the data, especially when we're working off of time series of data, not just like a median like this that tends to be a little cleaner than the individual images. And so one thing that we could do is apply a terrain correction algorithm. And what that is basically a model that gets applied to the data, and removes the effect of topography. If you think of my example of throwing a tennis ball at a slanted wall, what the correction algorithm does is create a model to basically prop up that wall again, at least make it appear to us like it's propped up vertical and it's no longer sloped away from us. I should add that this is another model on top of this data. So it's obviously you cannot actually remove the topography, but you could do a pretty good job of removing these topographic effects. So in step 8, we're going to apply a topographic correction algorithm to our collection of Sentinel-1 images. And so this is a approach that was implemented by a scientist, Andreas Vollrath. I have a link to the paper in the tutorial. And so we're just applying their model, basically. And so we're loading their code, and we're going to apply their code to our data. This is one cool functionality of Earth Engine, is that if other people make their code accessible, then other people could just load it and apply it. It's actually in my repository right now because I had to fix a bug, an error. But I just want to make sure you know that this is not my code. And so what this step 8 is doing is, for all of the images in our original collection, we are applying a slope correction, terrain correction algorithm. And all the rest of this is doing is just recalculating the median and clipping it to our study area, recalculating the difference image, and then adding it to the map with the same color stretch. So I'm going to load both the uncorrected, which is this one, and then the corrected, so we can see the difference. So this is the original uncorrected data. You could obviously see the mountains. Once again, this could be okay. Some applications you're okay with, you could be okay with having the terrain effects. But we found that this is just another layer of noise in the data that helps to get rid of for our application of forest monitoring. And I'm just sliding on and off the corrected image. And you could basically see that the mountains go away. The topography goes away. It flattens the image out completely. And so now for us, for the user, we're now able to use an image that essentially represents Madagascar without any topography. And this is helpful because it just removes the added noise that comes with topography. I should note that one thing that is very common with radar processing that I'm not going over in this tutorial is applying a spatial filter to try and remove noise. So there's a whole field of radar processing that involves what they call de-speckle analysis. So speckle is a common attribute of radar data that is basically it could also be called the salt and pepper effect, or just noise in the data. This is due to a lot of factors. But it's just due to noise in the scattering that's being observed by the sensor. I'm not doing it here because in my experience when working at least with time series data, it's not completely necessary, especially when doing the other filtering we're doing here. I do want to note, though, that if you do want to explore spatial filters for cleaning up the data, there's one really important thing that you should know about this data collection on Earth Engine. And that's that it's in log scaling. So going to the Earth Engine kind of window about this collection, hidden all the way at the bottom, it says that the final values are converted to decibels via log scaling. And I want to point that out because if you're doing spatial filtering techniques, that needs to be done usually on linear scaling. So if you know, one easy approach is to take a spatial mean, like an average, and an average should be done over the linear scaling rather than the log scaling. So I just wanted to point that out because I've made that mistake. And I don't want you to make the same mistake that I've made. So step 9 is a little bit different. I just want to demonstrate how you would get this data off of Earth Engine. I wasn't sure how long this tutorial was going to take. So there's a couple more advanced features after this. But I wanted to make sure that I was able to demonstrate exporting. So that's why it's kind of in the middle here. The way you export data on Earth Engine is through an export task. Step 9 is basically defining the parameters for how you want to export data. What I'm defining here is that I want to export our terrain corrected median image. I'll get back to the region, but that's the area of exporting. Scale is spatial resolution, so 10-meter resolution. The description is the name you're giving the file. I'm just calling it image Sentinel-1. And exporting to Google Drive to a folder called Sentinel-1. So I just described this. I gave a bunch of screenshots in the tutorial, but the region's defined by a geometry called export region. And that can be found in your geometry imports, which is this tab on the map right here. And so there are two geometries defined. You can ignore the first one. I was basically trying to point, it's just a location, a mountainous area that I ended up not using. But the second one is called export region. And you could turn it on and off with this checkbox. I'm going to turn off the extent. And what this geometry is it's a yellow box that defines where we want to export our data. We could change this in a couple ways. When you click on it, you're given the option to expand it or move it. You could also delete it and draw a new box somewhere else. I could also use a different layer completely. So I'm going to create a new layer. You could rename it export region 2. Draw a box somewhere. If I wanted to use export region 2 instead of export region, I would just need to change it in my export parameters in step 9. So export region 2. We also have already defined a geometry that's the country extent called Madagascar in step 1. We could use that here instead. That'll be the whole country. Or just one of these little boxes. And when you run this, this is initiating an export, or it's setting up an export task. And tasks are a way that you basically process things that are not loading on the fly. So if you have a process that will take a long time to load, and too long, it won't load on the map, you want to save it for later, you will want to export it as a task. And you could either save it as an Earth Engine asset or export it to Google Drive, where you could download and use in ArcMap or QGIS or anything. The way that so this kind of sets up the task. The way that you submit it is by going to your task tab. You'll see that there is this bar that's named the description we gave it, image Sentinel-1. If we click run, we get to re-specify our parameters. So the resolution, what folder, the file name. If you want to instead save it as an asset, you would select asset here. And you submit the job by clicking run. So now you would get process, radar, composite for whatever the study area and time period you specified. Okay, so we have 20 minutes. I have there's 3 more sections. I would like to try and get to at least 2 of them. And I apologize if I go a little fast. This is all being recorded, so I want to make sure that you're able to go back and watch this and repeat what we're doing here. The next section so far we've just been looking at the data and looking at composites that are a little hard to make sense of if you're not familiar with the data. What I wanted to do with step 10 is actually relate it to the landscape, and specifically relate backscatter to tree cover, to try and get a sense of what different backscatters mean as it relates to different tree cover on the landscape. And so the first part of step 10, we're loading a NASA product. It's called the Global Forest Canopy Change product, I believe. We could once again copy the path and look at more information in here. Global forest cover change. And what this is a measure of tree canopy cover every 5 years. And so it's 2000, 2005, 2010, 2015. And so it goes from 0 to 100. You know, you can get a sense from this image here. It's percent tree cover. It's obviously not perfect. It's global. It's made using Landsat, but we found it to be pretty good, surprisingly good, actually. And so what I want to do is relate this tree cover layer to the backscatter values that we are calculating for Madagascar. And so what step 10 does is it loads this layer for 2015, and it samples 500 locations to get at each location what's the backscatter in VV, VH, and the difference layer, and what is the tree canopy cover, and then it plots them against each other. And so, you know, this first line of code is loading up that collection of tree canopy cover. The next one is sampling the combined layers. And then we're creating a series of charts, and we're going to print those charts. And they should make sense once we actually look at them. So in these plots, I'll make them a little bigger. On the x-axis is canopy cover in 2015. On the y-axis, for the first plot is VV backscatter. For the second plot is VH backscatter. The final one is the ratio. So the signal is not incredibly clear. There's a saturation and it's noisy. But what you could generally see is that with increasing canopy cover, you get increasing backscatter. You would get a pretty similar plot if you change the x-axis to biomass, for example. In that for C-band radar like Sentinel, it will saturate pretty quickly. But the general trend is that as you increase in biomass, as you increase in trees in general, you get higher backscatter value. There's not a very clear signal with the difference. And so I think this is important to know for forest monitoring, because we want to know how we could detect change. And so we need to know what the data will look like when we go from forest to non-forest, or forest to less of a forest. And generally speaking, if you go from more tree cover to less tree cover, you're going to get a reduction in backscatter. And so we could see that in another way using step 11. And I think this is the last step that I want to go through today. This kind of sets us up for what would be the whole nother section of analysis, which is actually doing the change detection. Okay, so I just ran this whole mess of code, and now I'll go back and explain it. There's another global data set that was created from Dr. Matt Hansen from University of Maryland in his lab group that is tree cover loss globally. It is like any global product, it's not perfect, but I think it's a pretty good guide to try and find areas of actual tree cover loss. And so I want to look at what the time series of data looks like for an area that undergoes deforestation. And so to find areas, I'm loading up the Hansen data set and putting on the map areas that have changed after 2016. And now what this step does is it will, when you click, it added this panel to the map. Now, when you click, the time series of that location will load on this panel. And so I wanted to get the full collection of Sentinel-1 data, not just the subset between our start and end dates. So I redid the developing of the collection and the terrain correction. But we already did this. I'm just redoing it here for the full time period. created a panel. That's this white box. Added it to the map. And now when you click somewhere, the time series, it'll take a second to load. But the time series of the, I believe, VH bands will load here on the chart. And so what we could do is load the Hansen data set and try and find areas that have undergone forest change and look at what the corresponding time series looks like for that location. So I just clicked randomly. I don't know where this was, but now I'm going to click somewhere that looks like maybe was actually forest change. And so as this is loading, I should say, this processing we did today, part of it was to get that median image. It's just a usable composite that's pretty clean and is for the whole study area. The other is to do a standardized pre-processing of the whole collection so that we could get these time series data and then run an algorithm like CCDC on top of this data. And so I just clicked on one of these change patches. And what you would expect to see is a decrease in backscatter from the change. It's a little hard to tell from this example, but that could have occurred right around November 2018. I'll see if I can find a better example. Okay, so this is a better example. We can see pretty clearly in 2020 that there is a considerable decrease in backscatter, which to me would suggest that there was a forest loss event there, based off the fact that we know that backscatter will increase with tree canopy cover, that a decrease like this would represent a loss event.
Eric,
And
would
so-
this be more visible if you pop that out to its own window?
Yeah, a little bit. Thanks, Sean.
Sure.
So we can see pretty clearly here in 2020 that there is a sizable shift in backscatter. These are all the observations for one pixel that I clicked on. And it's worth noting that this is a noisy time series, even after the processing we did. Also, the change, the shift, is only really visible for maybe half or 1 year. So what we try and do with CCDC is take this time series, fit a model to it, and look for this shift in the time series and label that as a change. The final step, which I'll let you do on your own and for the sake of time, is to actually create a very preliminary map of change using CCDC. The reason we're out of time, I think that the actual use of CCDC and making sense of the results and selecting parameters would be a whole 2-hour tutorial on itself, at least. Which I would be happy to do. I'd be certainly happy to do, or at least provide this similar form of documentation and code. I chose not to go that route today because I really feel it's important to look at the data ahead of time rather than just looking at maps of change you get out of a process. But now that we've created our collection of Sentinel-1 data that's processed in the way that we want to use it, it's basically a matter of just applying it to the algorithm and then formatting and making sense of the results to get maps of deforestation or alerts, whatever you want to call them.
Okay,
So,
thanks very much, Eric.
Yeah.
I mean, I do agree that leaving the CCDC part of this for a separate call, or at least cutting it off here, it's a natural break. Now we've had a chance to explore the data, and applying the automatic detection of disturbances, that's a totally different subject, and it's already 5:30 in Madagascar. So it does seem like a natural stopping point. It depending on Carol's and her team's desires, maybe we can turn that into at least the first part of our next meeting, going through the code that you've presented here, and maybe talking about some of the parameters for the algorithm if they're interested. So this has been great. I've learned a lot. I'm sure everyone else has too. Thank you, Eric.
Good. Yeah, and I hope that this was helpful. As Sean said, I'm more than happy to follow up with more detail on CCDC or more detail. I had to cut out a bunch of things from this. I realized in making the tutorial that just how complicated this is, especially the first time doing it, how many steps there are. So would love to hear feedback, whether you want more processing, more examples, CCDC, anything like that. I would love to hear it.
Okay, is there any feedback or questions from the Madagascar side on what we have seen today?
Great. Well, if questions, oh, sorry, go ahead.
Do you hear me?
Yes.
Okay. It's Carol. Hi, Sean and Eric and
Hi, Carol.
Young. So, excuse me because I was late for this session, but I could still follow the majority of the steps to follow. And maybe as a first step, if the team have some questions concerning this tutorial and this presentation, maybe they can ask it now. Or do you prefer if we write by email?
Up to you. That would be fine. You know, I'm sure
Okay.
that people might want some time to process
Maybe
this. So.
yes. Maybe just a few questions for me. Concerning the availability of the imageries, the radar, Sentinel imageries. How about the availability of these imageries? And concerning the session, maybe as you told as you told us, we still need other sessions, another session for to know more about the CCDC.
Yeah. So you tell me what would be helpful with the CCDC part of it. If you are interested, which it sounds like you are, I'd be happy to do this again, but for that, we're just focusing on the CCDC. I could also provide the code and tutorial without having to listen to me going through it, if it'd be easier for the group to do it kind of on their own. That it totally up to you. Whatever would be helpful. And can you repeat the first question, please, about the availability of Sentinel-1 data?
Yes, this question is about the availability of Sentinel-1 radar imageries. I mean the period in which the Sentinel-1 radar imageries are available.
Yeah, so
and are they free of use?
So they are free of use. All of the data is free for us to use. In northeastern Madagascar, the data starts around 2016. The Sentinel-1 data globally, in some places, is available as early as 2014. But that really depends on the location. That it's consistently available after midway through 2015 to 2016.
Just to follow up on Carol's question, the box that you are showing now shows that the data start in March of 2015, but the density of observations seems to be much greater after 2017. Does that affect the CCDC process at all?
Yeah, so the first year or two of data, there was less observations being recorded. The CCDC algorithm will perform better and the alerts will be created faster with more data. So the quality of the monitoring will improve after around 2017 when there's higher frequency in data. It doesn't mean we can't do it before then. It's just not going to be as good.
Okay, thank you.
So probably the first alert can be detected from 2016 in Madagascar, given the density of the imagery.
Yeah, I agree. It might be different in southern Madagascar. I'm not sure.
Okay, thank you very much for the answers.
Yeah. Yeah, thank you for the questions, and thank you everyone for attending. Yeah, I like doing this, so thank you.
Yeah, very grateful, Eric, for preparing all of this. This is it was very clear. The examples, I mean, I was following along. They worked well. Questions for Madagascar, Carol, Harry, and others.
Oui, bonjour à tous. Merci. Merci pour la présentation, c'était très enrichissante. Ma question, c'est que par rapport au traitement sur CCDC, comment savoir pour le changement de classe avec le nuage du point de tout à l'heure, vous dites qu'il y a fait un changement en 2020. Et comment savoir visuellement cet changement? Merci.
So let me share my screen again. So we're looking at a time series here of, let me make it bigger. This is a time series from 2015 to 2021. CCDC will fit a model to this data. You know, it'll fit a model from 2015 to 2017. And as soon as the observations start to look different from that model, which happens in around 2020, a change will be flagged. That's a very simple overview of how it works. And I would suggest, you know, we spend a lot more time looking into exactly how that works and what the maps look like, simply because we're out of time here. But this really simple answer is that CCDC works by modeling the time series and identifying where the data starts to deviate, to change from that model, and placing a change right there. And this is just one time series of one location. It's doing it for every single location for your study area. So across millions of time series, it is doing this change detection.
I would ask your team to suggest, maybe not right now, but by email within the coming days, suggest dates for maybe a follow-up where Eric can explore with us the details of what he just said.
Yeah.
Ok, ben, on va voir avec l'équipe pour définir la date. Et peut-être qu'on va vous envoyer un email ultérieurement.
Great.
That would be great. And maybe at the, sorry.
Can I ask some question? So,
Yes, sir.
okay, I was just wondering if all the rate points you've shown on the map could be exported, or because I think it will be very useful for us to know to have these data. Or we will do it on next session of call.
So in step 9,
Sorry. Okay.
in step 9, I show how to export one of the layers we create. It's possible to do this process for any of the data. I just showed an example of one. But next time I could go over how to do it in a more general sense, because everything we do on Earth Engine can get exported to be used on your computer. But I would suggest going back to look at step 9 in the documentation.
Okay, thank you.
Yep.
The related question, how to the Madagascar colleagues, how familiar are you with Google Earth Engine? I would, if not, it will maybe a session on Earth Engine itself. Would that be useful?
Jan, could you repeat again the question, please?
So the question was to our Madagascar colleagues, if a general overview of Google Earth Engine would be useful for another session. And just the general functionality, things like exporting, importing, stuff like that, if they thought that would be useful.
Oui, oui, c'est bien nécessaire par rapport à notre travail ici. Justement, avec Google Earth Engine, c'est intéressant.
Okay, thank you. Maybe we will consider that in the next stage after, or maybe during Eric's continuation of this radar processing module. Okay, I do know that it is getting late, so I want to bring this to a close. We will look for your suggestions. We have several things related to the launch of Landsat 9 in the middle of September, so maybe in the second half of September, if you could suggest follow-up dates for this meeting, we will come back with suggestions for an agenda for our next meeting. Does that sound okay to the Madagascar team? Well, I presume it does. So again, I want to thank you, Eric, and thank also Kathleen for your excellent translation. And I guess we will be in touch in about a month or maybe a bit more.
Yeah, thank you, everyone. Special thank you, Kathleen. Makes a big difference.
Eric and Shen, maybe it will be better for us to have the session in the last week of August, or in the beginning of October, because in September we are full.
Okay. I would suggest the beginning of October. That will give you a chance to explore. I have recorded this session. Will give you a chance to explore the document that Eric has sent, all of the code that he shared, and I guess by the beginning of October, you will have had a chance to explore the radar data, and that will be a good point at which we can present the automatic change detection part of the code. So yeah, maybe I will share with your team some options for dates, or you could suggest dates to us by email for the beginning of October.
Okay, it's fine. We will share our proposition by email.
Great.
Sorry.
Thank you.
I was wondering if you could share to us the record of this session, because it will be useful to us to review all the session, maybe.
Yes, definitely.
Thank you in advance.
Okay, great. Well, it was a pleasure to hear from all of you today, and we will look forward to talking to you in early October. Thanks, everyone.
Thanks, everyone.
Thank you.
Thank you, and see you next time.
Take care.
Good night.
Bye.